Hey everyone, welcome to this explainer. Today we're diving into a pretty wild mystery right at the heart of NMR spectroscopy. We're looking at a scenario where perfectly symmetrical, seemingly identical protons in a molecule can suddenly produce these unexpectedly confusing, messy NMR spectra. We're going to unmask what we call the deceptive twins of NMR.
So can two perfectly identical protons act completely differently? I know, it sounds like a total trick question, right? You'd think if two protons look completely identical on paper and live in the exact same chemical environment, they should interact with the world in the exact same way. But as we'll see today, these deceptive twins of organic chemistry might look alike, but when you drop them into a magnetic field, they actually hold entirely different conversations with their neighbors.
Okay, let's look at the roadmap for today. First, we'll quickly review the basics of NMR spin. Then we'll define chemical equivalence before getting into the big plot twist, magnetic equivalence. After that, we'll see these rule breakers in action, and finally, we'll talk about why all this equivalence stuff actually matters.
All right, kicking things off with Section 1, the basics of NMR spin.
So just to quickly set the stage, remember that many atomic nuclei behave literally like tiny spinning bar magnets. A hydrogen nucleus, a proton, has a spin quantum number of 1/2. Since it's a moving charge, it creates its own little magnetic field. When you put it in an applied magnetic field, it's forced to pick a lane. It can either adopt a +1/2 state that aligns with that external field, or a -1/2 state that totally opposes it. Now, before we turn on that magnet, those spin states are degenerate. Basically, they sit at the exact same energy level. But the second we hit the switch and apply that external field, boom, those states split. The aligned state drops down to a lower, happier energy level, and the opposed state gets bumped up to a higher one. And that energy gap right there, that's exactly what we're measuring in the NMR spectrometer when those nuclei absorb radio frequency energy.
Moving right along to Section 2. What is chemical equivalence?
All right, now that we've got our magnets spinning, let's set our baseline expectation for molecules with multiple protons. Chemical equivalence simply means you've got protons hanging out in completely identical chemical environments. Think of them like identical twins living in the exact same house. They experience the exact same average magnetic environment. This usually happens because of some plane of symmetry in the molecule, or just free rotation around a single bond that averages everything out. And because they experience the same local diamagnetic shielding, they precess at the exact same frequency, giving us the exact same chemical shift.
To put that into perspective, think about highly symmetrical molecules like acetone or TMS, tetramethylsilane, which is our trusty universal zero-point reference. All the protons in TMS are chemically equivalent thanks to symmetry and free rotation, so they just give us one beautiful sharp absorption peak. But if a molecule has sets of protons living in distinct, completely non-equivalent environments, well, each unique set is going to give you a totally different peak. Makes sense, right? Pretty straightforward.
But here's where things get tricky. Section 3, the magnetic equivalence twist.
I want to read this quote straight from the source material because honestly, this is the exact spot where so many of us, students and seasoned researchers alike, get completely tripped up. Quote, magnetic equivalence has requirements that are more stringent than those for chemical equivalence. Yeah, just because protons are chemically equivalent, there is absolutely no guarantee they are magnetically equivalent. So, what does it take? To be magnetically equivalent, a group of nuclei have to pass two incredibly strict tests. Test number 1, they must be isochronous. That's just a fancy way of saying they have identical chemical shifts. That covers the chemical equivalent side of things. But the second rule, that's the kicker. They must have equal coupling to all other nuclei in the molecule. I'm going to say that one more time because it is absolutely crucial. They must have equal coupling to all other nuclei in the molecule. Their J values to any specific neighboring atom have to be perfectly identical. Let's look at a perfect example of a molecule passing with flying colors, chloromethane. It has a beautiful threefold axis of symmetry and free rotation. So all three hydrogens share the exact same chemical shift? Check. And since there are literally no other adjacent hydrogens on this one-carbon molecule, by default, all three hydrogens are equally coupled to all adjacent nuclei. I mean, they're coupled to a null set, but it counts. So they are both chemically and magnetically equivalent. The whole shebang.
Okay, let's see what happens when things go wrong. Section 4. The rule breakers in action.
So what happens when a molecule fails that strict second test? Enter our deceptive twins. These are protons that have the right symmetry to be chemically equivalent, but they completely fail the coupling test. It's like those twins we talked about earlier, living in the same house, but they actually talk to the neighbors next door totally differently. Let's look at some real-world examples from the spectrometer.
Now, what's really interesting about this slide is how simple physical distance just destroys magnetic equivalence. Take a look at a para-di-substituted benzene ring, where the top and bottom substituents are different. You see that plane of symmetry right down the middle, right? So the proton on the top left, HA, and the top right, HA', are chemically equivalent. But look at their relationship to the bottom left proton, HB. HA couples to HB across 3 bonds. But HA'? It has to couple to HB across 5 bonds, all the way across the ring. And since a 3-bond coupling constant absolutely does not equal a 5-bond coupling constant, HA and HA' do not couple equally to all the other nuclei. Boom, magnetically inequivalent.
Here's another classic rule breaker, 1,1-difluoroethene. The two hydrogens, A and HB, are chemically equivalent, but check out how they couple to one of the fluorines, Fa. A couples to Fa in a cis geometry. Meanwhile, HB couples to Fa in a trans geometry. And as we know from the basic rules of NMR, trans coupling constants are inherently way larger than cis coupling constants, meaning 3J trans is absolutely greater than 3J cis. Once again, because they have different coupling constants to the exact same neighboring atom, these hydrogens are totally magnetically inequivalent.
Oh, and we also really have to watch out for restricted rotation. In something like 1-chloropropane, the two hydrogens on carbon-2 are magnetically equivalent because free rotation around those carbon-carbon bonds just averages out their magnetic environments and their couplings. But if you attach massive, bulky substituents that physically stop that free rotation on the NMR timescale, suddenly those dihedral angles get locked into place. The coupling constants become permanently unequal, and just like that, our perfectly equivalent pair instantly turns into magnetically inequivalent rule breakers.
Which brings us to our final part, Section 5, Why Equivalence Matters.
So we've caught the rule breakers, but why do we actually care about magnetic inequivalence? I mean, why do you need to know this when you're staring at a screen trying to decipher a messy spectrum for your own research? What is the real-world impact of these protons having different interactions?
Well, the crucial point is this. Failing that magnetic equivalence test leads to messy, highly complex data. When protons are completely magnetically equivalent, they behave nicely, they don't split each other. But when chemically equivalent protons suddenly become magnetically inequivalent, the math behind your spectrum goes totally out the window. They start throwing out unexpected peaks and wildly complex splitting patterns that basically defy simple analysis.
It's literally the difference between first-order and second-order spectra. In a nice, weakly coupled system where protons are completely magnetically equivalent, you get these beautiful, predictable first-order spectra. The good old N+1 rule works like an absolute charm. But the minute magnetic inequivalence rears its head, you cross over into a strongly coupled system. The N+1 rule just completely breaks down. Your clean, textbook doublets and triplets morph into these chaotic second-order multiplets that are a total nightmare to assign without advanced analysis or some serious correlation tables.
So how will you spot these hidden quantum interactions in your own lab work? The next time you're looking at a deceptively simple, highly symmetrical molecule, you really need to ask yourself, are these protons truly identical, or are they deceptive twins having secret coupling conversations behind your back? Honestly, if tiny, simple molecules can hide this much complexity, just imagine what kind of magnetic chaos is lurking inside the massive proteins or complex polymers in your advanced research. Definitely something to think about. Thanks so much for joining me for this explainer, and happy analyzing.